so far from our group and from others from all around the world. Then talk about some of the current challenges for quantum network. Then I'll talk about some ongoing projects that utilize the Argon quantum network and other links that we have at Argon. And then I'll summarize and take some questions, and we can do some discussions afterwards. So first I wanted to start with what quantum communications is all about, right? So essentially it started with the goal of making classical communication more secure, right? The QKD, the quantum key distribution, which many of you may be familiar with it, because it uses the principles of physics, right? I mean, so it's actually used to create inherently secure keys. Say, for example, the quantum signals are weak. I mean, if somebody is eavesdropping on the link, it's easy to find out, right? So the keys, rather than using like the current, if you look at the current security, it's actually based on complex mathematics, right? So it relies on NP-complete problems, and if you want to decode the key, it will take forever even using the largest supercomputers, right? So rather than relying on complex mathematics and the need for using a huge computer to decode, and it will take forever, so the quantum keys, they rely on the principles of physics, right? So that's why it's inherently secure. So there are like commercial products that are available, right? So that you can use to generate quantum keys. But then there are limitations to it, right? So the quantum signal, you cannot put that through amplifiers, right? I mean, so if you look at the classical signals, once every, like, I don't know, 100 kilometers or so, something like that, right? Somewhere around that ballpark, you need amplifiers. You need amplifiers to amplify the classical signals, but the quantum signals cannot be put through the amplifiers, right? So because of that, you need quantum repeaters, and we don't have any quantum repeaters yet. So because of that, there is a distance limitation, right? I mean, so there is a distance limitation. So the quantum keys, you can distribute up to like 100 kilometers, 130 kilometers, something like that. So that's the limitation, but the quantum communication goes beyond that, right? I mean, so the QKD is sort of well established, even though there are some limitations. So we want to look at quantum communications beyond the QKD, beyond the quantum key distribution, right? So if you look at the quantum computing technology, that's still at a very preliminary stage, right? So if you look at quantum computers, the largest quantum computers these days are have 100 qubits. I mean, which is hardly enough to do any complex problems. I mean, even to solve tie problems, it's not enough, right? I mean, so you need millions of qubits. So one of the things that quantum networks can help is connect these quantum computers, right? So connect smaller quantum computers to form a larger quantum computer, right? So that's what we call by distributed quantum computing. And then also quantum networks has applications in quantum sensing. Quantum sensing is supposed to be powerful than classical sensing, and then if you actually are able to gather data from multiple sensors, so if you are able to do distributed quantum sensing, that's supposed to be even more powerful, right? So those are some of the applications of quantum networks. So, but then the thing is, we need capable quantum networks, right? So that's, again, quantum networks is still in a preliminary stage, but we want to advance the state of the art. So just for those of you who are very new to this, don't know much about quantum computing or quantum networking, just wanted to briefly introduce what a qubit means, right? So qubit is the basic unit of quantum information, and it's a two-dimensional complex vector, right? So the difference between like qubit and the classical bit is it's the qubits are probabilistic, right? So it can be it's hard to say what state it's in, right? I mean, so when you measure, it boils down to one or two states, but it can be in an in-between state until you measure, right? I mean, that's what some people call superposition. It can be in both state 0 and 1, but that's very confusing. But the thing that I want you to get from that is it's probabilistic, right? I mean, so until you measure, you don't know what exactly the state of the qubit is, right? So, and then there are different types of qubits. I mean, the two key qubits, right? It means flying qubits. What I mean by flying qubits is photonic qubits. So photonic qubits are attractive because you can actually produce that in like a room temperature, right? And then like it's easy to communicate. So the photonic qubits are attractive from that perspective. But then you don't really get to do computing with that photonic qubits, right? So you basically need to convert them to matter qubits because there are like few platforms. People are exploring different platforms for quantum computing, but it's still not clear which technology is going to win out, right? I mean, so there is superconducting based platforms, ion traps, neutral atoms. So these are all matter qubits, right? So and then another key thing, if you want to understand like quantum computing and also quantum networking, the entanglement is a key phenomenon, and that's a fascinating phenomenon. You don't have an equivalent of that in the classical world, right? So you may actually have heard that, I mean, three physicists got Nobel Prize for demonstrating this phenomenon of quantum entanglement, right? So what exactly is quantum entanglement, right? So it's a fundamental concept in the quantum information theory, right? And so what I mean by that is, let's actually take this example to just show you, demonstrate. I've simplified this, but just for understanding purposes. Say if you are in, when two particles are independent, right? So how they behave, when they are independent, how they behave, when they are entangled, how they behave. This picture actually shows that. So when they are independent, so they have equal probability, like meaning, so you can be in, like the system can be like a circle, and I mean, let's say it can have two different shapes, right? I mean, circle and a square, and then so the thing is, you have these four probabilities, right? I mean, so the two particles, so one in circle, so the system one is in circle state, system two is in square state. Likewise, there are four possibilities, and they four have equal probability to be in that state, right? In one of those combinations. Whereas if two particles are entangled, then they either both of them are in circle or both of them in square. You don't know which one, but so they are dependent, even if they actually split. I mean, so you entangle two particles and you split them apart to a long distance, right? So even then, they have this dependency. So that's the phenomena of entanglement, and that actually makes the quantum communication interesting. And so still, to be honest, people still don't know all the applications that you can create when quantum networking becomes really available, right? I mean, but then even when you actually, if you think about the classical network, when they created the network, they didn't imagine all the applications that we have now, right? And so the hope is that there are few applications that we are envisioning now, but when the network becomes a reality, there will be much more application that we are not imagining now. So I did talk about some of the applications, distributed quantum computing, quantum sensing, but there are other things as well. In quantum key distribution, we talked about it. And then there are some other things as well where you can actually even actually speed up the classical communication, and also like it can actually help you to do a much more precise clock synchronization. So with that brief introduction to quantum networking, I'm going to move on to talk about the Argon quantum network, right? So at Argon, we have a campus scale quantum network wherein we are connecting 5 different buildings, right? So we have some devices, we have different platforms. So there are physicists working on different kinds of platforms. I mentioned about the different kinds of matter qubit platforms, superconducting, ion trapped, neutral atoms, right? So there are physicists working on those kind of qubits. So we are basically connecting those different platforms using a fiber-based network, right? So and then we have a hub where we have an all-optical switch, and then we have a single photon detectors. The thing about quantum networking is like, so you're basically transmitting a single photon, right? I mean, so the single photon has a state in it, has information in it. That's what you're transmitting. So you need single photon detectors, and you need entangled photon source. So you need to create entangled particles, right? So that can be used to. So one other phenomenon, fascinating phenomenon, is the quantum teleportation, right? So what I mean by that is, so I mentioned about the quantum entanglement. So you entangle particle, you actually move that particle to, like, let's say site A and site B, right? They're at a distance, right? So then what you can do is, so these two particles are entangled, which means they are dependent on each other. Now you can actually transmit an arbitrary quantum state from A to B without physically transmitting that state. You still need to transmit a classical information, but you are not transmitting the quantum information physically through a medium. So that's what is called a quantum teleportation. So since you still need to pass on a classical information, the information still cannot move faster than light, but it's still a fascinating phenomenon because you are not moving the state physically over a medium, right? So you can basically, once you have entangled particles, you can demonstrate quantum teleportation. So this phenomena of quantum teleportation has been demonstrated, right? So the idea here is, again, so even though the quantum teleportation has been demonstrated, this demonstration was only at a photonic level. But you need to teleport matter qubits, right? So that's what we are striving to do. So anyway, so we want to use this infrastructure to do those demonstrations. So we've already demonstrated entanglement distribution on this network, but we want to use that to teleport quantum states, right? So this is what we did, actually. So we were able to distribute entangled particles between two different buildings. And what we also demonstrated was, even on a single fiber, we were able to use different wavelengths and actually distribute multiple pairs of entangled photons between two systems. So then, so the thing that I talked about was the argon quantum network, and the argon quantum network is actually connected to a Chicago-wide, so what we are calling as a Chicago metropolitan quantum network, right? So my colleague Ashif actually was giving the talk earlier, right? So he's from Fermilab. So we have a strategic advantage in the sense that Argonne and Fermilab are quite close to each other. They are both in the Chicagoland. They are only like 30 miles away. So no other labs are that close to each other. Maybe Berkeley and SLAC, but none of the other labs are close to each other, right? And we also had an advantage in the sense that back in the 90s, there were a lot of dark fibers that were laid when the classical internet was picking up, and when we were actually looking at, it actually goes before my time at Argonne. But my boss, Ian Foster, and others, Rick Stevens and others, actually, they did a demonstration called I-Way, right? Information way, right? So that kick-started the distributed computing and grid computing for science. So when they were doing that project in the 90s, they actually got several fibers laid, and some of the fibers between Argonne and Fermilab were not used. They were remained as a dark fiber, they were not laid, right? So I mentioned that the quantum signals are very weak, right? Which means that it cannot really co-propagate with classical signals. I mean, I shouldn't say it cannot, but it needs some careful calibration if you really want to coexist, and it's still not clear how much they can coexist. So people are studying that phenomenon. So can we actually have classical signals and quantum signals go on the same fiber? So since it's early and there is no clear demonstration of this coexistence yet, so it's better to have like dedicated signals for quantum communication now. So for that, the dark fiber really helps. So we were actually using that dark fiber between argon and Fermi, and we also have fibers going from Argonne to University of Chicago, which is also again like roughly 30 miles from Argonne. And we also have fiber going from Argonne to Starlight is an internet exchange point that is in downtown Chicago. That's a little bit longer. That is actually taking a circuitous route. So that's about 50 miles. That still can be used for quantum communication, right? So we have that, and then from Starlight there is a dark fiber going into Northwestern. So we have a relatively complicated or relatively large metropolitan scale network. So we are still working on more demonstrations, but what we've done so far is we were able to distribute entanglement between Argonne and Fermi, right? Likewise, Northwestern guys were able to distribute entanglement between Northwestern and Starlight. So, and then one other thing that we did was I talked about like the demonstrations that we did within Argonne. So this is a midway point between Argonne and Fermilab. So when that link had some issues in the last mile. So during that time, we were able to loop through that midway point and get it back to Argonne. So this is one of the first entanglement distribution that we showed, what we call as Argonne quantum link that goes outside Argonne and coming back. And then once that problem, the last mile problem was fixed, what we did was we were able to distribute entanglement between Argonne and Fermi, and we were also able to send some classical signal on the same link, same fiber. So what we did was we used, there is this multiple bands in the telecom fibers, right? So there is C band, O band, and C band is primarily used for classical communication. So what we did in this case was we used C band for quantum and used O band for classical, mainly because the attenuation is less on the C band. So we were able to show that we passed clock signals on O band and quantum signals on the C band, and we were able to show that still we were able to distribute the entanglement. So it's not just us, there are like several other people all over the world. There have been some demonstration between Italy and Spain, I believe, and then China has done some demonstrations, and there is also the Calgary, Netherlands have done some demonstrations as well, like similar to what we've done. And then this Calgary experiment is what actually showed the teleportation. Like they were able to teleport the quantum state in a campus scale, like 8-kilometer network. And then Oak Ridge National Lab has also done some demonstrations. So the thing, they've done, like a lot of people have done this demonstration. So what's the limitation, or what are the challenges, right? So all these demonstrations are mostly point to point. Not mostly, all of them are point to point, right? But if you guys are experts in networking, and some people actually don't really consider the point-to-point link as a network, right? So you need to have at least 3 nodes or more nodes to call something as a network, right? So we want to go beyond that point-to-point. So we want to go like use multiple nodes, demonstrate distribute entanglement between multiple nodes, and also move state, teleport state among multiple nodes, right? So that's something that we need. And also these demonstrations are carefully calibrated or manually done, right? So a lot of manual steps involved. So we really need to automate these things, right? So how do we actually automate these things? Because the thing is, these demonstrations in some sense, they are lab demonstrations. These are all like pretty much like physics experiments. So we want to move them out of the physics experiment and make it into like network experiments, right? So, but the thing is, there is no clear abstraction on how do we actually interact with these devices, right? So there is entangled photon source, there is single photon detectors. So how do we interact with them? So we need to create the abstractions. And also the devices are also not there, right? There is no quantum repeater, there is no quantum memory. But even the devices that exist, we need the abstraction. So we want to develop a control plane that is fully automated, right? And also, like I talked about multi-node, and we also should be able to support multiple entanglement distributions, which sort of simulates multiple users. So when the network becomes real, you want multiple users to use that network, right? So we want to support multiple users, and then we want to go, so even though we've done some simple demonstrations in the metropolitan scale, so we want to do more, and then we want to go beyond metropolitan to regional scale. So this is a new project at Argonne. We're calling it as InterQNet, right? So the idea behind this is to address some of the challenges that I mentioned, right? So we want to be able to fully automate the entanglement distribution, right? And also, there are, scalability along multiple dimensions, right? So I mentioned about this point-to-point, and also I mentioned that all these demonstrations are at the photonic qubit level, right? So we want to go beyond the photonic qubit to incorporate matter qubits, right? So that's why we call it as a heterogeneous network, right? So we want to connect different platforms and enable people to distribute entanglement between platforms and eventually move the quantum state between different platforms. So there are two key components in this project. So the first one, we call it InterQNet Achieve. So this is where I talked about three different platforms, right? So those are the three key platforms. There's superconducting qubits, ion-trapped qubits, and neutral atoms, right? So luckily, we have physicists at Argonne working on these three different platforms, and there are also collaborators who are working on similar platforms as well, right? So we, in collaboration with other institutions like University of Chicago, University of Illinois at Urbana-Champaign, and Fermilab. So our goal is to basically, so even though we have that Argonne quantum network which connects these different platforms, we still not able to distribute entanglement between different platforms yet, right? So our goal as part of this project is to enable that entanglement distribution among these different platforms. But there are several challenges with that, right? I'll talk about those challenges and our plan to address them, right? So Shu Han is a colleague who actually is working on the superconducting devices. The problem with these different matter qubit platforms and the photonic network is that, like I said, so we've demonstrated, people have demonstrated this quantum communication or entanglement distribution in the C-band, right, which is 1520 to 1550 nanometers, something, somewhere around that range, right? So, but then these superconducting platform produce microwave qubits which are at a different wavelength, right? So which means that we need to do frequency conversion. And in other words, there's a process called transduction that needs to happen, which can actually convert these microwave qubits to photonic qubits, right? And that's not easy. There are a lot of challenges, and they're still fabricating devices that can actually aid with that process. So that's something that's ongoing. And likewise, so this one is actually, at least from that point of view, this one is easy in the sense that this has a transition, erbium ions, when you actually pass the laser through it. It has an excitation, so it can actually excite photon in the C-band, right? It can excite the photon in the 1520 nanometer, right? So from that perspective, this is easy. But then again, like fabricating that device, there are challenges. We know it can actually produce that, but in order to make it reliably produce that, it's not easy. So it's still trying out different materials to enable that in a reliable fashion, right? And then the third one is the ytterbium atoms, right? Ytterbium atoms, again, there are three people working on it. There is an argon physicist and a person at University of Illinois and University of Chicago. So this one, interestingly, this has an excitation in 1389 nanometer, right? So which is closer to the C-band, but we still need to, so it can actually have that excitation in 1389. But again, when it's excited, how long it can remain in that state, right? I mean, so that again, that coherence time is very less. So there is challenge in that, like, so how long we can actually maintain that state, and also, like, how do we actually convert that from 1389 to the C-band, right? So for that, we again need a quantum frequency converter. So we have another collaborator, Prem Kumar, at Northwestern University. So he's working on the quantum frequency conversion. So wherein we can actually convert that 1389 to 1520, right? So then the idea is basically, so you have an ytterbium atom, erbium ion, and superconducting microwave qubits, right? So basically you excite them, you get a photon out of it, right? So which means that you produce a photon that is entangled with an ytterbium atom. You produce another photon that's entangled with erbium ion, another photon that's entangled with microwave qubit, right? And then you actually do a bell-shaped measurement on these photons. Basically, you get these two photons, you entangle these two photons. Through that, you can actually entangle. Say, for example, the photon that comes out of the erbium ion and the photon that comes out of the ytterbium atom, you make those two photons entangled, and through that, you make the ytterbium atom and the erbium ion entangled with each other. So that's the basic idea. So I talked about this a little bit. So for all the demonstrations that has happened, there are a lot of manual steps, right? So you need to do several steps, like there are multiple nodes involved. You send in a signal to a node, you get that node to do something. So that all has been done manually, so which we want to actually orchestrate it through an orchestrator to get to make this in an automated fashion, to basically make it a routine process, right? I mean, so if manual effort means, I mean, you have to have someone who actually, I mean, monitors these things and logs into different systems and do that. So first step, what we want to do is at least, I mean, script that steps out, right? And then we look at what other challenges we have and automate it one by one. So, so that's sort of the device level things, right? I mean, so that's the lower level, device level things. How do we connect and what's the plan for it? And you also need to be looking at the software stack or the architecture, a higher level architecture for scalable quantum networks. How do you actually develop one, right? The issue here is that since we have an example in the classical networking case, right? I mean, so because we have a classical internet, we have the software stack, we have an architecture. So we have 7-layer OSI stack. So we have a 5-layer TCP/IP stack, right? So what people are doing is, oh, okay, so we have that. Let's just use the same architecture, right? Let's just have that 5-layer architecture. Let's just have that 7-layer architecture, and let's try to fit in to the quantum communication, right? So what we believe is that that's fundamentally problematic, because there are a lot of difference between the classical communication and quantum communication. You don't want to blindly replicate the classical architecture, just adopt that for quantum communication, right? So this is an example kind of layered architecture or different planes that we came with for one of the projects. But I'm not in any fashion advocating that this is the way to go, but this is one sample architecture, right? But what we argue is that the key thing that kicked off the classical internet, right? The classical networking is this hourglass-shaped architecture, hourglass-shaped model, right? So there is the neck in the hourglass, and that's the IP in the classical networks, right? So different types of devices, they all speak the IP protocol, right? I mean, so there is a interface that you get from all the devices. They provide the IP interface, right? Likewise, different applications, right? All of them can make use of that IP interface to talk to these different devices, right? I mean, so there are other layers in that stack, but that's to simplify it. So that's fundamentally made it like any kind of device can get on the network, right? I mean, as long as they speak IP, right? So likewise, can we adopt a similar hourglass type architecture, right? I mean, so at least that's something that we are advocating. We think that the hourglass model will help with the quantum communication, quantum network architecture, but we still need to do research on what is that neck? What is that neck going to be here? Like IP, what is it? Is it the entanglement distribution, or is it something else, right? So we want to do that research as well. So this forms the crux of the second piece of the InterQNet project, right? So I mentioned InterQNet project. InterQNet project Achieve deals with the physical network that can enable communication between different platforms. And then there is a InterQNet scale part where we want to develop a scalable architecture, or where we want to at least study different scalable architectures, right? But there is a fundamental problem, right? How do we actually study this scalable architecture? I mentioned that the quantum network, the real quantum network, is in a very preliminary state, right? There are not many devices available. So I mentioned that you cannot amplify the quantum signals. In order to amplify quantum signals, you cannot pass through the regular classical amplifiers. You need quantum repeater, right? But so quantum repeater, people have actually developed theoretical models for it. So there are 3 generations of quantum repeaters that have been proposed, but there is no quantum repeater in practice available yet. A lot of people are trying to build one, and we are trying to build one too. We believe that the ytterbium atom platform that I mentioned is a good platform for quantum repeater, so we are actually trying to build that. But all of the quantum repeater work is still in preliminary state, right? So we don't need a quantum repeater. So how do you actually do scalability studies? And if you want to do scalability studies, you want to scale the distance, you want to scale in terms of, again, like the heterogeneous platforms. I mean, I mentioned about the heterogeneous platforms, but it's still very preliminary, right? How do we actually conduct large-scale experiments to study like what kind of architecture would be good for quantum communication, right? So that brings us to like what happened with the classical network, right? So the classical network, if you look at the classical network, simulations played a huge role, right? So there was this NS series of simulators, right? Network simulators, which won a huge award actually. Don't know if I mentioned it in here, but they won an award like few years ago in terms of like, so for the role that it played in shaping up the classical internet, right? So what it helped was, so there were different protocols. So if you look at TCP, it has evolved significantly, right? I mean, so the additive increase multiplicative decrease based congestion control algorithm went through a lot of iterations, right? So different TCP protocols, different kind of lower level technologies, right? I mean, ATM, SONET, and all those things. So the simulators actually played a huge role in evaluating the pros and cons of these different platforms, different architectures, different protocols, right? So likewise, what we argue is that simulators can play a huge role in the evolution of quantum networks as well, right? Because you have a lot of different choices. So if you look at memory, there are different, so many different choices. Quantum repeaters, different choices. Error correction protocols, many different choices. So, and then again, qubit platforms, there are many different qubit platforms, many different protocols to distribute entanglement. So all of these can be studied through a simulator, right? So, I mean, this just talks about like different advantages of the simulator, what all you can do. So you can, like I said, I mean, you can do the, study the architecture design. You can actually find alternates in terms of for the platforms. So there are many different advantages, many different things that you can do with the simulator. So that brings us to our work in this space, right? So I mean, my background is in classical networking, and I did some research in classical networking, but I was actually a user of all the latest and greatest in the networking, all the technologies that you guys build. So I'm a user of it, and like in a lot of cases, early user of it, right? So my background is primarily in, I mean, I knew the classical networking quite well. And about 6 years ago, in the US Department of Energy, they started talking about quantum networks, right? And they did a first workshop, and I attended that first workshop, and then, I mean, at that time, I didn't know anything about quantum. I mean, even now I only know little, but at that time I didn't know anything, and I was thinking, how do I contribute to this quantum networking effort, right? So that's where, like, okay, the simulator is probably the early step that I can do, and after that we started thinking about the simulator. We started slowly building the simulator. It's called Sequence. Now it has actually evolved quite a bit. I mean, it's an open source project. There are users for it from several countries. I mean, I would encourage you guys to take a look at it. I mean, if you see a need for, like, if you want to play with how quantum communications work, this is a good starting point. So again, we did a modular design. Basically, you need hardware models, right? So there are devices. What are the key devices? Photon source. You need to create entangled photons. So you need to have an entangled photon source, a model for it. You need to detect that photons. You need to have a model for it. And you need a memory. Because the thing is, you want to scale it, so you need the repeater. So since there are theoretical models for it, we implemented those models, even though real physical device is not available, right? So those are the bottommost thing forms the models, and then you have some protocols. So there are protocols to distribute entanglement. So we implemented those protocols, and then you need to manage the resources. There is a resource manager piece, and then you need applications. So there is QKD, well-known or well-established application. So that's there. So we implemented some applications. We implemented both network level protocols, application level protocols. So that's all available in Sequence. And then, so basically what you can do is you can feed in a network topology. You can basically set the properties of the optical components. So there are simple models for fibers, models for classical communication, and then you can actually choose the protocols. There are protocols that are available. There are protocols that are contributed by people, the protocol that we developed. So all of them are available in the Sequence simulator. And then what we did was we did some experiments. We tried to mimic this metropolitan scale network that I talked about. So we did that. And then what we realized was, when we actually started to scale, when we actually increased the traffic, when we increased the number of users, when we increased the number of nodes, we ran into scalability issues with the simulator. So we parallelized the simulator as well, so it can actually use a cluster of nodes and run faster. So that's also there. Yeah, I mean, the parallelization gives a decent speed up. I'm not going to go into the details of it. So what you can actually do with it, right? So I talked about some architectural design choices. So what could be that, right? So we still don't know how do we actually pass the controls in a quantum network, right? I mean, so the demonstrations that we have done so far is by doing out-of-band control. Like you send control signals out of band to these devices and have them actually distribute entanglement and transfer or teleport state. But you can also do in-band, right? So doing in-band control is tricky. So you need to have timing synchronization. But that's something that you can study in the simulator, right? I mean, so you can actually have an in-band control versus out-of-band control, implement both of them and study the pros and cons of it, what are the trade-offs involved in it. And one other thing that we also did in the simulator is that, I mean, entanglement is a key resource in quantum network. Can we actually pre-generate entanglements so that when a request comes in, so basically when a request comes in to create entanglement between A and B could be at a longer distance, right? So you need to have like entanglements at smaller length. So there is an intermediate node at C, you create entanglement from A to C and C to B. So this I didn't really talk about it. So you can actually create like smaller entanglements to create a long distance entanglement. So you can use multiple small distance entanglements, and there is a concept called entanglement swapping. So you have entanglement between A and B, you have entanglement between B and C, and if you actually do a measurement at B, if you try to entangle those two particles, you actually get an entanglement between A and C. So that using that, you can actually form a longer distance entanglement. So since you have to do that, and entanglement generation is a probabilistic process. Like I said in the beginning, everything in quantum is probabilistic. So you need to, I mean, when a request comes in and then you try to generate the entanglement, it can take longer time, right? So you want to like adaptively pre-generate entanglements. So that's something that we've done. So with that, I will summarize and be happy to take questions and have some discussion. So quantum networks hold a lot of promise, but things